In this video, we'll introduce ridge regression, a shrinkage method that improves on ordinary least squares regression by constraining the coefficient estimates. The two shrinkage methods covered on exam SRM are ridge regression and the lasso. We'll cover ridge regression in this video and tie it together with the lasso in the next video. Let's start with ridge regression, also known as L2 regularization. Recall that in ordinary least squares, we find the coefficients beta 0 through beta p that minimize the residual sum of squares, or RSS. The RSS measures how well the model fits the observed data. However, when the predictors are highly correlated, the OLS estimates can become unstable and sensitive to small changes in the data, making the model unreliable. Ridge regression addresses this problem by adding a penalty term to the loss function. This penalty, lambda times the sum of the squared coefficients, is called the shrinkage penalty. It constrains the size of the coefficients, reducing their variance and preventing overfitting. The ridge regression coefficients are now obtained by minimizing the RSS plus the shrinkage penalty. Notice that the penalty term only applies to the slope coefficients beta 1 through beta p. The intercept beta 0 is not penalized because it serves as the baseline level of the response variable. Here, lambda is a non-negative tuning parameter. We'll explore the role of lambda in more detail in the next section. The tuning parameter lambda controls the strength of the shrinkage penalty. Its purpose is to balance fitting the training data well and keeping the model coefficients small to avoid overfitting. Here we have 5 coefficient estimates computed from a generated dataset. When lambda equals 0, the ridge fit matches standard OLS, so the coefficients are exactly the ordinary least squares estimates. As lambda increases, the penalty term grows, and the coefficients are recomputed by solving the ridge normal equations. Watch how the fitted coefficients change as lambda moves from 0 to 500. The transparent outlines show the original OLS coefficient sizes for comparison. As lambda approaches infinity, all coefficients approach 0, effectively removing the predictor's contributions to the model. This results in a model that is overly simple and may underfit the data. To summarize, when lambda is 0, we get standard OLS. When lambda is positive, the predictor coefficients are shrunk toward 0. And as lambda grows to infinity, all predictor coefficients approach 0. The key challenge is selecting the right value of lambda to balance bias and variance. The L2 norm measures the magnitude of the coefficient vector and is a useful way to represent the penalty term in ridge regression. The L2 norm of a vector beta equals the square root of the sum of the squared components. Geometrically, this is the Euclidean distance of the vector from the origin in p-dimensional space. The shrinkage penalty in ridge regression, lambda times the sum of beta j squared, can be written as lambda times the L2 norm squared. Minimizing this penalty shrinks the coefficient vector towards the origin. To measure how much ridge regression shrinks the coefficients, we can compute the ratio of the L2 norm of the ridge coefficients to the L2 norm of the OLS coefficients. When lambda is 0, this ratio equals 1. As lambda increases, the ratio decreases, reflecting stronger shrinkage. Before applying ridge regression, it's important to understand how the scale of the predictors affects the results. There are 2 scale facts to keep straight before applying ridge regression. Standard OLS regression is scale equivariant. If a predictor xj is multiplied by a constant c, the OLS coefficient beta j simply scales down by 1 over c. The product beta j times xj, and therefore the fitted value, does not change. However, ridge regression is not scale equivariant. The shrinkage penalty penalizes higher coefficients more than lower coefficients, so scaling beta j down by 1 over c changes the penalty contribution for that predictor. Lambda prevents a linear mapping because it treats all beta j values equally regardless of the scale. To address this, we standardize the predictors before applying ridge regression. Each predictor, xj, is transformed by subtracting its mean and dividing by its standard deviation. This ensures all predictors are on the same scale, so the regularization is applied uniformly. Ridge regression offers several advantages over ordinary least squares. First, ridge regression reduces variance by shrinking coefficients, which can lead to a lower test error than ordinary least squares. Second, the penalty stabilizes coefficient estimates when there are many predictors, especially when predictors are highly correlated. Third, adjusting lambda helps optimize the bias-variance trade-off, which can improve generalization to new data. And fourth, ridge regression is computationally efficient. It fits a single model for any value of lambda, compared to best subset selection, which must search through 2 to the p possible models. Let's build geometric intuition for ridge regression by visualizing what the penalty really does to the coefficients. The ridge regression objective can also be written as minimizing the RSS subject to a budget constraint S. Although the derivation is beyond the scope of this video, we can intuitively understand the equivalency between the constrained form and the penalized form as 2 different ways of controlling the same trade-off. The constrained form directly limits the size of the coefficients, while the penalized form from earlier indirectly encourages small coefficients by adding a cost for large ones. To visualize what's happening, consider the case where we have just 2 coefficients, beta 1 and beta 2. Recall that a formula of the form x squared plus y squared equals r squared defines a circle centered at the origin. Replacing x with beta 1, y with beta 2, and r squared with the budget parameter s gives the ridge constraint, beta 1 squared plus beta 2 squared less than or equal to s. Any allowed pair of coefficients must lie inside this circle. The green point marks the unconstrained least squares solution, the pair of coefficients that minimizes the RSS with no penalty at all. The green ellipses around it are RSS contours. Every point on the same ellipse gives the same residual sum of squares, and the RSS grows as we move outward from the center. The ridge solution is the point where the smallest possible RSS contour just touches the edge of the constraint circle defined by the constraint formula we looked at earlier. We can't do any better on the RSS without leaving the feasible region. This contact point is the ridge regression estimate, beta hat r. Notice that because the circle has a perfectly smooth boundary, the touching point almost never lands exactly on one of the axes, so neither coefficient is set to exactly 0. This is different from the lasso, which intercepts the constraint region at an axis, setting one or more coefficients to exactly 0. We'll cover this in another video. The takeaway here is that ridge regression does not perform feature selection, since all coefficients from the original model are retained. Now what happens if we shrink the budget parameter s? The feasible circle gets smaller, so the ridge estimate must have a smaller overall coefficient size. This is directionally equivalent to increasing the tuning parameter lambda, whose purpose it is to balance the trade-off between fitting the training data well and keeping the model coefficients small to avoid overfitting. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.